In this segment on income distribution and income inequality, I'd like to actually take a look at a few of the different ways or metrics with which we measure inequalities within our society. First, let's talk about something referred to as the genuine progress indicator. This indicator is something that's actually formed and somewhat championed by one of our professors here at the University of Utah as part of a team of academics and professors throughout Western Europe and the United States. And this particular professor is Professor Gunsili Berek. Gunsili is a noted feminist economist, but also relatively pragmatic in many respects. And I have a tremendous amount of respect for Dr. Berek. She's done some work on this genuine progress indicator, which is really a rather holistic index that takes into account many different elements that help us understand utility and lifestyle and health and income and political connectedness and civic connectedness, and all of these very important and sometimes very rich cultural attributes, as well as some very numeric, quantitative financial attributes, all of which conspire to help us understand the utility level of an individual or a household. And the genuine progress indicator is an index that brings all of this in to help us understand, are we improving, becoming more highly developed, or are we devolving and going backwards within our economic and social development? If you're unfamiliar with the genuine progress indicator, I would encourage you to Google that. You'll find some very rich information, and much of this is attributed to Dr. Berek within our University of Utah Economics Department. Another index is the Human Development Index. This is used by the United Nations and the World Bank. It's not nearly as holistic. It takes a look at income levels, life expectancies, trade openness, and political openness and freedom, if I recall correctly, and develops an index. But it's a relatively accurate index. When we see when that index value increases, that development is improving, average lifestyles or median lifestyles and standards of living are improving, and income inequality is reducing. We are converging to some kind of towards an equal state rather than diverging with this big income gap. There are three other metrics that are used very heavily. One is the Kuznets curve, developed by economist Simon Kuznets, in 1954. The next is the Lorenz curve, which was developed by U.S. economist Max Lorenz in 1905, and it's been used as heavily in engineering as anything else for that matter. It's interesting, engineers picked up on this because it's really simply a way of looking at distributions across a whole, and engineers like to look at this in terms of load distributions and bridges and such. And then a numeric representation of the Lorenz curve, referred to as the Gini coefficient, developed by Corrado Gini in 1912. Gini was a noted Italian sociologist. So let's look first at the Kuznets curve. You might have seen the Kuznets curve with respect to environmental economics if you've taken any of those classes. The Kuznets curve with respect to income inequality would suggest that we're looking here at income inequality from low levels to high levels on the y-axis, and per capita income as we go from low levels to high levels on the x-axis. It would suggest that as income per capita increases, that for developing economies, income inequality increases as well. So income gains, per capita income gains, average income gains, the average person, not the median, but the average, these are then positively correlated with some increasing income inequality, but only for developing economies. And that at some point we reach an inflection point, a turning point, at which the economy becomes more fully developed. This might be where an economy could qualify to become a member of the OECD, the Organization of Economic Cooperation and Development. And beyond that, per capita or average income gains begin to tell us something about begin to represent lower levels of income inequality. So as we get wealthy enough as a economy, then we take and use some of our per capita income, distribute it more widely, and use it in a more egalitarian way. Well, there are some problems with this. This is a very interesting construction. Kuznets was a noted economist. He was well beyond his time, but at the same time, he was wrong in this item. We don't see this inflection point where we go from increasing at a decreasing rate to decreasing at an increasing rate. What we do see, though, is that we do hit a turning point. It might look more like this, though. We reach some period where we're relatively flat, and then we begin to increase again. Now, it's interesting. We think that this is because of effects of globalization, and Kuznets in the 1950s couldn't necessarily adequately foretell the effects of globalization, capital, both physical, financial, and human capital mobility. And so his expectation of what might happen as income per capita increases, that we would see for developed economies, we'd see income inequality decreases, has not necessarily been the case. We did see an improvement, but then we've seen that give way to great divergence and worsening again. The Lorenz curve is a very different kind of formation, and I use the Lorenz curve heavily in different research because it gives us an opportunity to see differences in distributions within a group. So if we think about this, the Lorenz curve measures on its x-axis percentage of households, and I have this separated off my tick marks in quintiles: 0 to 20%, 40%, 60%, 80%, then 100. And then we get to see on the y-axis the percentage of total income or total household income. So percentage of households and percentage of total household income. Now, I said that this is the y-axis. It's over here on the right side. We're used to seeing the y-axis on the left side. It's the same axis. It's just been telegraphed to the right. So don't think of it as being a different axis. This is still just the x and the y-axis. And what we see here is that if we go from 0 to 100% of our households and then 0 to 100% of the income of those households, we can draw a line from this point at 0 to this point at 100, and that line would be the line on which we have perfectly equal distribution of income, or the line on which we had, let's say, the top 20% of households had 20% of the income, or 40% of households had 40% of the income. So perfect equality. And this then is referred to as the line of equality, this line with a slope equaling 1. This is the line of equality. Well, this might be representative of a perfect level of socialism or communism. And I say a perfect level. We've never observed such a thing, by the way. We've seen communism. We've seen socialism. Neither of them have prospered. They've ultimately failed in each case. But that may be more a function of human beings being rem and being inside of these structures, always wanting more for themselves, and then that corrupting the structure than the methodology or the concept of the structure itself. Regardless, what we see is that this line represents equality. And when we have an unequal distribution of income, we see that some curve develops beneath this line. And this curve then gives us some visual representation of income inequality within our society. Let's think about what this is telling us. Let me get rid of a few of these lines so it cleans it up here just a little bit for us. And what we're seeing then is, in this case, if we have a point on this curve here, that is suggesting that in this case the bottom 20% of households had some income distribution, looks like maybe 8% of the income. And that the next 20% giving us a 40%, that then takes us up here something along the lines of the totals maybe 18% of total income. And the next 20% taking us to 60, we then see that maybe this is 36% of the total income. And then as we go to the next quintile, or the 80% quintile, we see this moving up where we have maybe 60% of the income, and then the final 20% of the economy has what looks here to be about the final 40% of income. So we see that the 20%, the upper 20% of households have 40% of the income. If this Lorenz curve were an accurate representation of an economy, it isn't necessarily. It's just here to be representative for you. But this tells us something of the Lorenz curve. Here's a couple of interesting things about the Lorenz curve. I often have students ask me if the Lorenz curve can be above the line of equality. Can it arc above the line of equality? Well, conceptually, it cannot. For it to do so, it would mean that perhaps the bottom 20% of households had more than 20% of the income, in which case they would cease to be the bottom 20% of households. So structurally, it cannot be above the line of equality. The closer the Lorenz curve itself is to this line of equality, the less unequal the distribution of income in the society. The further away it is, let's say that if we had a Lorenz curve all the way down here, the further away it is, the more unequal the distribution within our society. And so we can see that the Lorenz curve can be a very powerful comparative tool. The curve in and of itself is somewhat informative and illustrative, but comparing it with other groups or other points of time is maybe just as powerful. Let's say that this Lorenz curve maybe is the United States Lorenz curve in 2015, whereas this curve perhaps was the Lorenz curve for 1960. And I know that the values for those periods of time would not give these exact Lorenz curves. This would be far overstated in terms of the change. But you can see some of the dynamics of change. Or you could see maybe a Lorenz curve or income inequality for white Americans and income inequality for black Americans, or the well-educated versus the poorly educated, or the healthy versus the unhealthy. So it's a great tool that lets us look at a population at different periods of time, or different populations. Maybe this is the Finland and this is the United States, both in the same year. So it's a great comparative tool. In fact, if we look at this, we can see a little bit more of a relationship here. Once again, we're looking at our line of equality. We've got the same formation, although this particular graphic was created by Hilda. That's not a person, that's an organization, by the way. And we see that we see wealth inequality compared to income inequality for the U.S. in 2010. We do see that income inequality and wealth inequality are positively correlated, where the more unequal the income, the even yet more unequal the wealth. So they're positively correlated. But this is U.S. income and wealth in 2010. If we look at changes for the U.S. over time, we can see some quintile values here, the bottom 20%, the top 20%. And we see the 1968 mean or average household income and 2010 mean or average household income. We see then these percentiles selected for these years. And we can see then, as I've suggested, that income inequality has increased in these decades since 1968. In fact, the greatest part of that increase since 1980, of course. And we see that 1968, we had a fair level of income inequality within our society, but by the time we hit 2010, that's moved meaningfully to the right. So we have yet that much more so. This takes us to the Gini coefficient. One of the things that you would probably recognize is that this Lorenz curve, as informative and illustrative as it is, if you had this in a published paper or in a research paper, or even on a research poster perhaps, is going to take a fair amount of space. Yes, it tells you something, and it's a great comparative tool, but it's not a very efficient tool in this respect. So the Lorenz curve takes a lot of space. A gentleman by the name of Gini in 1912 said, well, maybe we can give a numeric value to this. Maybe we can value it in such a way that it tells us something at least as illustrative and within a much more efficient mechanism. So Gini suggested that if we create a value for the area above the Lorenz curve and below the line of equality, and we call that area A, and then we also take and create an area below the Lorenz curve and above or the various axes, so between the curve and its axes, and call that area B, we can create a coefficient which is A divided by A plus B. And that value then will tell us something about income inequality. Well, you can see then in the Gini coefficient space that the smaller the area of A, or the smaller the distance between the line of equality and the Lorenz curve, so the smaller A becomes, the less unequal the society is. So in this case, a small Gini coefficient is a relatively unequal society, such that we can think of a society which might actually have perfect equality. That's conceptual, or conceivable, if you will. So we might even be able to see a Gini coefficient that is greater than or even equal to 0, where there is no A. If we were actually a perfectly equally distributed economy, there would be no value of A. It would all be B, in which case the Gini coefficient would be 0. But it can clearly be greater than 0 as well. But I don't know that we can really conceive of a Gini coefficient of 1, because 1 would mean that A comprises the entirety of this right angle triangle, the entirety of this area. In which case, if we're thinking even in terms of the percentiles, forget quintiles for a moment. Forget dividing an economy up in 5 equal parts. Let's divide it up in 100 equal parts, or 1,000 equal parts, or 1,000,000 equal parts, or even 311 million equal parts. There would still be at least one earner, one individual. If all others had 0, kept us right on this lower bound on our axis, at least one would have all the income or all the wealth, such that the Gini coefficient would have to be at least a tiny bit less than 1. Now, maybe so tiny a difference that it would be a rounding error out to the 10th decimal place, but it could never be 1. There is some disagreement amongst economists on this, but if you think about it intuitively, that disagreement probably is simply a disagreement of rounding issues. Well, how do we measure this? You might know calculus perhaps, and you know that you can take an area between two curves using some calculus and realize that by doing some integration you can create a value. Well, that value happens to be a little bit challenging in this case, because yes, we do have a equation that we could have for the line of equality, but if we're actually looking at this in terms of quintiles in 5 equal parts, we don't really have this nice smooth curve. What we have is a series of what should be straight lines. They'll likely be anything but straight as I try to replicate them, but a series of straight lines that then give us an approximation of a curve. So that's actually would be 5 different equations that each have their own ranges, such that doing integration to find area of A would be a little bit difficult. But if you think about it, we know what the value of A plus B is. If we go from 0 to 100%, and as I recall, 100% is the same thing as 1.0, and we've gone again from 0 to 100%, so again, 1.0. As this A plus B is simply a right angle triangle, then this becomes 1 times 1, so base times height, divided by 2, or 1 divided by 2, or 0.5. So as it turns out, A plus B is a constant, and it equals 0.5 or 1/2, always. In any Lorenz curve Gini coefficient formation, A plus B always equals 0.5. And so we don't even have to calculate our denominator. So how do we get to B, or rather to A then, given that this is kind of a difficult space to value? Well, I'm going to suggest that we play some algebra here, and if A plus B equals 0.5, then what do you say we realize that A equals 0.5 minus B? And B, as it turns out, has kind of an interesting set of shapes. If you look at B, it's a triangle, and then if we give some lines here, we see that it's simply a series of rectangles and triangles, because this wasn't this nice sweeping curve. This was 5 straight lines. If we're dealing with quintiles, it would have been 10 straight lines if we're dealing with deciles, 100 straight lines if we're dealing with percentiles. It's really just a series of triangles and rectangles. Well, so B is the sum of some right angle triangles plus the sum of some rectangles. And you'll see in a moment, when we have a quintile separation, the sum of these triangles is simply 0.1. And so all we really need to calculate is the sum of the rectangles. Let's look at how we might think about this a little bit further. Let's suppose that we have some values here that are helping us understand the formation of our Lorenz curve, that the bottom 20% of our economy has 9% of the overall income. In this case, the next 20% has 11%, so total that's 20%. The next has then 15%, so total that's 35. The next has another 23%, so total that becomes what, 58%, and such that the top 20% of this particular economy, based upon these quintile values that I'm representing, the next 20% has 42%, so that gives us actually the entire 100% in our economy. Well, if we think about it, how do we begin to value these triangles? I suggested here that the sum of the triangles was simply 0.10. How did I do that? Well, what I did was I thought about these right angle triangles and how we create their values. Think about this with me for a moment. Each one of these, if we're thinking about these as 0.2 is being the same as 20% or 0.09 being the same as 9%, what we really have for this sum of our triangles is we have 0.2 times, in this case, 0.09 divided by 2, plus 0.2 times 0.11 divided by 2, plus 0.2 times 0.15 divided by 2. I can't even stand this here. I need to clean this up for us. I apologize. That was times 0.11 plus 0.2 times 23% divided by 2 plus 0.2 times 42% divided by 2. Well, if we want to make this much simpler, we can factor out 0.2 divided by 2 because that's something in common with each one of these triangles. So 0.2 divided by 2, and then we're going to simply add up the amounts that were left over because this was additive, of course. So 0.09 plus 0.11 plus 0.15 plus 0.23 plus 0.42. And you can take a moment and add those up, or you can just intuitively look at it. We're talking about this plus this plus this plus this plus this, which immediately you see that equals 100% or 1. So what we really have is 0.2 divided by 2 times 1, or we have 0.10. Now, this happens to be the case when we're dealing with quintile separation. The sum of the triangles when we're dealing with quintile separation is always going to be 0.10, but only when we're dealing with quintile separation. If we were dealing with decile separation or percentile separation, it would be slightly different than 0.10, but whatever it is for that separation, quintile, decile, percentile, it will be a constant for that type. Let's look at this a little bit more. You can see that I've replicated these values here, showing us the sum of the triangles. I've gone through some of that same math, but then I use some of the same thought to think about, okay, how might we consider the sum of these rectangles? Now, the rectangles now are going to be the leg or the height times the base. Well, the height, if you think about it, is cumulative. If we had 9% for the first quintile and 11 for the second, then this first rectangle that we're dealing with really represents something happening within the second quintile, and it's going to be 9% times 20%. The third quintile's rectangle would be 20%, again cumulative times 20%. The next would be that 20% plus this 15 for a sum of 35% times 20%, and so on. And we only have 4 rectangles. So if we look at this, we have 0.2 times 0.09, 0.2 times 0.2, 0.2 times 0.35, 0.2 times 0.58. We can factor out the 0.2, and it's simply 0.2 times these heights of each of these 4 rectangles, or in this case 0.2 times 1.22, or that equals 0.24 or 244. So the sum of our rectangles is 0.244. The sum of the triangles was 0.10. The B was equal to the sum of the rectangles and triangles. So in this case, given the values that I showed you, we have an area of B of equal to 0.344. And if A is equal to 0.5 minus B, then A is equal to 0.5 minus 0.344, which is equal to 0.156, which then lets us be able to actually motivate our Gini equation, our Gini coefficient of A over A plus B. So it's 0.156 divided by 0.50, or we have a Gini coefficient of 0.312. That might seem a little bit complex to you, but really what could have been many calculations, a calculation for A plus B, a calculation for each one of these triangles separately, which is a separate term all divided by 2, and then a calculation for each one of these rectangles separately, actually turned out to be 2 constants, A plus B being 0.5, the sum of the triangles being 0.1, and then a relatively simple calculation for the sum of the rectangles, which then led us to this Gini coefficient of 0.312. Finally, it's probably worthwhile to recognize the United States Gini coefficient currently and over time. We're looking at a 2010 Gini coefficient for each of the major nations within the OECD, the Organization for Economic Cooperation and Development. These are Gini coefficients after taxes and income transfers. This would look much different before taxes and transfers. In fact, it would be even more exaggerated before taxes and transfers. And after taxes and transfers, the United States has the highest Gini coefficient of all of these nations measured within the OECD. Interestingly enough, Finland and Denmark and Norway consistently have the lowest. These are the very high northern European states, very cold, but rather egalitarian in most of their considerations and policies. But the United States isn't just highest by a little bit, it's highest by a lot. And which means we have the worst income inequality after taxes of any of the rest of the OECD. In fact, if you looked at this before taxes, it's yet worse still. If we look at the changes in the Gini coefficient from the early 1960s or mid-1960s through the early 2010s, we see predictably that the Gini coefficient, even though it's had some ups and downs, of course, it has predictably have a trend line that we can easily plot that's very much an upward sloping trend line, simply representing a worsening income inequality in the United States for these time periods, and leads to the concern that many of us have as economists that as the Gini coefficient is getting worse, as income inequality is getting worse, as social and political unrest seems to be getting worse, then we may be reaching an inflection point where we reach some kind of a period of meaningful change. Hopefully it's peaceful and passive and progressive change rather than violent change. But these are the measures for the income inequality through the Kuznets curve, the Lorenz curve, the Gini coefficient, with a little bit of thinking about the genuine progress indicator and the human development indicator or index.